Okay, we go.
Well, we're not ready.
No, we're not.
Well, in that case,
Why don't I have control? Well, I guess we're ready. I can just use my thing here. We're in chapter 18. Open for the best.
oh wait a minute, you still got 2 minutes.
Well, I guess I have to do what Annette does and use my finger. So we're in chapter 18. And what we're going to do is we're going to throw 2 diodes into our circuit. So we've got a AC signal coming in. We got some fuse so that it'll blow in case we draw too much current. We have a center tap on our transformer, which means that if the center tap is grounded, then if I'm positive coming in, then I'm positive on the top and negative on the bottom. It allows us to cut our voltages in half, basically. And this guy allows us to transfer power to the load when I'm positive on the top, and that diode allows us to transfer the load when I'm positive on the bottom. When I'm positive on the bottom, I'm negative on the top, which means that diode's blocking it. So now instead of just sending half the wave, I get the full wave being sent from the transformer, and I'm not throwing away half my power. So when we were doing it before, we're throwing away half the power. Now we're not throwing it away. We're keeping it. So now we're seeing the obvious wrongness of our ways. Because when we have positive flow, we have to be going that way. And when we're seeing the positive half down there, current's going the other way. So thank you, author, for giving us the wrong flow. But now we're seeing that we have only half of the secondary peak in both of those cases, because we went in, whatever our voltage is here, let's say it's 120 volts and we have 25 on the output. Well, that 25 volts is cut in half. I only have 12 and a half going one way, 12 and a half going the other way, because I grounded the center tap, and it's going to be where my 0 is. So that's what's happening there. So if I look at this, what I'm doing, without the center tap being tapped, I'd have my primary guy would look like that. Oh, that's wonderful. And then my secondary would look something smaller than that. So I'm gonna do it half. But when I put a center tap in there, what's going to happen is I'm going to half it again, so that I only get half of it this way, and then that same half of it that way, which gives me the whole thing. So now my from there to there, if this was turned over, I'd have the whole thing. Did that make any sense? Or am I just mumbling up here? I still don't know why my marker's not marking. Oh well. That's what I'm thinking. That's what I'm thinking. My battery's dead.
Remember, plug it in. Yeah, did you plug it in last night?
No, it doesn't get plugged in. So the thing of it is I'm using the bamboo thing to write on with my finger, but I can't use my pen, which doesn't make any sense. Why can I move it with my finger but not with my marker?
Turn it on.
Well, I thought I did.
Try turning it off and on again.
The whole computer?
No.
I don't think so. Anyway, so now we're going to calculate the load voltage for the currents we have. Well, we have some peak voltage at the load, and that's going to be whatever the peak secondary voltage is divided by 2 because I put a center tap in the transformer, and then I'm going to subtract away a 0.7 volts. And the reason I'm taking away the 0.7 volts is because I'm going to lose 0.7 volts across the diode. So I have to take it away. So that's going to be the peak of the load voltage. So whatever the secondary voltage was, divided by 2 minus 0.7. Now, if I'm really, I have a real, there is no way I'm ever going to want to know the voltage average, right? Unless it's on a quiz or it's on something else. But in real life, we don't care about voltage average. We care about RMS voltage. So voltage average is a mathematical contrivance. I couldn't go out there and buy a meter to measure voltage average if I wanted to. Okay, but in a mathematical way, the average voltage is going to be, if I take that 2 times the peak and I divide it by pi. So if I divide it by pi, I'm going to get the average voltage peak at the load. But again, I don't really care too much about that because from a technical point of view, I'm not going to ever want to know that. So here we go. Here's the load voltage. I went in and turned my diodes around the opposite way. So now I'm going to get a negative full wave rectifier. I'm only getting the bottom half. So now my peak voltage at the load, the secondary peak divided by 2, but then there's still a plus 0.7 volts that they didn't bother to put there. So we should probably go back and put it there ourselves. And why the author left that out is anyone can guess on that, I guess. But so I need to add, because I'm negative, I'm going to have to add 0.7 volts. Okay, where were we? We're there, we're here. Okay, so now I can, went too far. Lost control again. Previous. Okay, so we're back to where we were. Excellent. Okay, so now I'm looking at the peak inverse voltage that's on the diode, because the diode's going to have some specification that I can't go above. And so I'm looking at that and I'm saying, well, the diode, if I have if this thing's rated for 24 volts AC, then the peak is going to be higher than that because that's an RMS value. So I'm going to have to multiply by the square root of 2 to get the peak value, and that's where they get the 17 volts. So I'm going to be 17 volts positive, 17 volts minus, and now the peak that any other diode would see is 34 volts peak across it. So if I had a diode that was rated for 25 volts, peak inverse voltage, I wouldn't want to put it in there, because if I did, I would just have the diode destroy itself. Maybe not today, maybe not tomorrow, but sometime in the future it would destroy itself. So 2 times the peak value that's on the load is going to be the peak inverse voltage across the diode. And then we still have to subtract the 0.7 because there's still a 0.7 drop across the other diode when we're looking at the peak voltage on the top diode. We still have to subtract that 0.7 because to get a more accurate number, if we so desire to do such a thing, which we might desire to do. Now, normally when we do a full wave rectifier, we use a full wave bridge rectifier, and we don't buy these diodes one at a time. We buy them all together, 4 together in a bridge. And now I look at this and say, well, if I'm positive on the positive wave, I come this way to the load, through the ground, pass that way to the other side of the transformer. If I'm the negative half cycle, I come this way, I come through the diode that way, I go through the load around this way, and then I come back to the other side of the guy. So because that was so crystal clear, we will do a capture of that. How come now I'm missing my capture thing? Alright, so this is what we're going to do. We're going to get rid of the extra stuff, and maybe the stuff that I'm supposed to have will be there. Won't that be nice? And it's not. Okay, well, that's just the way it is. So I'll do it again. On the positive half cycle, I come up, I have to go through D3, so I do. I go through the load, I come back through ground, I come up to D1, D2. I have to go through D1 this time, back to the other side of the transformer. On the negative half cycle, I come up through D2, through the ground, from the ground, through D3, back to the other side. I went the wrong way. Through D4, back to the other side. So on the positive half cycle, I'm going through 2 of the diodes. On the negative half cycle, I'm going through 2 of the diodes. What is my voltage drop across the 2 diodes? It's no longer the 0.7 of one diode, it's a 1.4. So now I'm losing 1.4 volts across my 2 diodes every time I do this. And now we can see those currents going one way or the other, and our currents are in fact going the wrong way on the picture. And if I had control of my computer like I'm supposed to have, I would be able to turn them around. But this, on the positive half cycle, I'm coming that way through ground, back up around. Negative half cycle, that way through ground, back up around. And the whatever the peak of the load is, that's going to be the secondary peak of the transformer minus 1.7 because I have 2 diodes I'm going to go through. Did I miss something? Peak inverse voltages. Okay, so our peak inverse voltages are not going to be as high because we are going through 2 diodes instead of 1 diode. So it's going to approximately equal the voltage across the source. But again, we're going to have 1.4 volts go away because I have the diode thing there. So here's a recompilation of half wave, full wave, and bridge rectifiers. Now, in the big picture of things, as technicians, we love bridge rectifiers and half-wave rectifiers and full rectifiers because they're things we can fix. About 10 years ago or so, we went to the switching power supplies in our computers, and now we have something we can't fix anymore, and we just have to throw it away and put a new one in. So there's not much value added between the old power supply and the new one. It's slightly smaller, still use the same amount of power, it costs a little bit more, but as a technician we can't fix it anymore. So from that point of view, it's not a good idea. But wasn't our choice, so we don't have that choice. Okay, now we're going to talk about filtering the output of our power supply. So we have the full-wave rectifier or the half-wave rectifier, and we're going to filter it. And what we're going to do is we're going to put a capacitor in the circuit, and the capacitor is going to charge on the positive half cycle, and then it's going to discharge until we get to the next positive half cycle, and then it's going to charge again, and then it's going to discharge, and then it's going to charge again. And as long as you are drawing, you're not drawing huge amounts of currents out of the capacitor, it's going to keep the voltage relatively high. So that's the whole thing. We are going to have a ripple voltage, and the ripple voltage is the little bit from when I get to the top to when I get to the bottom. So that little bit there is going to be my ripple voltage. So there's going to be a little bit of ripple in the DC, which may or may not be a problem, depending on how you look at it. If it is a problem, we'll solve it later. So now I've got a 100 microfarad capacitor and a 1 kilo ohm resistor, that's the load. I know the time constant of an RC circuit is RC, so 1 kilo times 100 micro is what?
Sorry, what was the question?
I don't know. I'm trying to do it in my head. What's the time constant of the circuit? So C1 times RL. So if I was on, I could go 100 double E minus 6 times 1,000. So I get 0.1 second. Okay, so my time constant is 0.1 second. The time it's going to take for the capacitor to fully discharge is going to be 5 time constants, which would be a half of a second. I have 60 hertz, it's going up and down 60 times a second, so that's how I'm keeping my capacitor charged. I'm charging it more than it can be discharged. It's being charged faster than it can be discharged, and that's the whole point. So I'm charging it, and let's get over here. So the time constant is RC, resistance times the capacitance, which in this case is going to be 1/10 of a second. And I need 5 time constants if I'm going to be fully charged or fully discharged. And so that means that I'm going to be fully discharged or charged in a half second, and my voltage that I'm applying is 60 hertz, and it's going to happen quicker than that. So 1 over 60 is 617. So 17 milliseconds. Well, that was good. 17 milliseconds is the period of the AC that I have coming in. 1 over 60. 1 over 60 hertz. Would be that 17 milliseconds. Well, that was crystal clear. I can just see that. Okay. Back to our slideshow. Okay.
Just broke.
All right, so that's what I'm going to do. I'm going to throw the filter of power supply. I put in a capacitor. The capacitor I put in has to be big enough so that I keep the voltages high enough so that my time constant isn't there. So when you open up a power supply, there's always a bank of 4, 5, 6, 10 pretty good sized capacitors in there, and that's what they're doing. They're being your filter. And now I've got some ripple associated with that, and depending on the size of my capacitor will depend on the size of not my frequency of the ripple, but how deep the ripple is. So the ripple voltage, and I can also change my load resistor too. And that's going to have some effect. Why they did both at the same time, I'm not sure. Oh, this is showing, I see. This is showing a constant capacitor. I'm changing my load, and this is showing a constant load. I'm changing my capacitance. And I get the same picture either way, so that's what that's trying to tell me. Now there's surge current associated with this guy as well. So I go and short it out, and I'm about to blow the fuse. I'm going to have some surge current. And the power supply needs to do this for a short period of time. So when I turn something on, I'm going to have some surge current going in to turn it on. When I turn something off, I'm going to have some surge going the other way as the power goes away. So what do? I discharge the capacitor for a little bit. The rectifier current is limited by the windings of the transformer themselves. So my transformer is a 1K transformer. I can't 1 kilowatt transformer. I can't get any more than 1 kilowatt through the transformer. And in fact, if I ground the secondary of a transformer, that ground is not seen on the primary side. All it's going to do is provide whatever the rating of the transformer is to ground, and it won't care. And why is that? Well, because it's a magnetic coupling from one side of the transformer to the other, I can't make the magnetics of the situation move any quicker. I can only transmit whatever the full load of the transformer is. That's as much as I can get out of it. Surge current is a high initial current because of I have a low voltage to begin with. I turn it on, boom. Surge current is limited by using a filter. Yes. So the other thing I can do is throw in an inductor into my filter as well. So I put my inductor in line, and that's also going to be used to limit my surge currents. So the capacitor is charging, the inductor is holding a magnetic field, and so it's going to discharge that magnetic field, allowing some current to go out. Filtered output voltages. So the DC voltage that I see on the output is going to be the peak of the voltage on the output minus whatever the half of the ripple voltage is. So I've got some signal that's giving me a peak. I got some ripple across it. If I divide it by 2, the ripple by 2, I can get what the DC voltage is. And that would be my first approximation. My best way to do that would be to put a meter on it and read what it says. That would be my preference. So here's my voltage on the output. It's doing something weird, and it's got some peak value, and it's got some smallest value. We're saying the DC voltage is halfway between those two values. My period, 17 milliseconds, 17 milliseconds, which is the period of the AC coming in at 60 hertz. Now, if I have a full-wave rectifier, then this happens twice every period, and now I'm down to only 8 milliseconds, 8.8 and a third milliseconds between my peaks of my ripple. Filter output voltages. So the ripple voltage is going to be the current going through the diode, the time between peaks divided by the capacitance. And let's see, when was the last time I used that in an equation that I remembered? No, I've always had to go look for it. Yeah, that's one of those equations I never remembered. 17 years, I still don't remember it. So if someone were to ask you for that on a test, raise your hand so I can put it on the board. And then I'd have to look it up. Yeah. That could be. Well, let's see. Let's check this out. Where are we? What's today? All right, we're going to 18.5 today. And then we're going to do some homework problems. So that's the plan. Filter output voltage. The full-wave rectifier produces half as much ripple as the half-wave rectifier ripple voltage. Now, why is that? Well, because it takes less time before it starts charging up again. So in the full-wave rectifier, I got half the cycle where I'm not charging at all. The full-wave rectifier, I fill in that hole. Filtering effect on the diode's peak inverse voltage. Well, what did we say? The peak input voltage, inverse voltage. What is this trying to tell me? Okay, on the positive half cycle, I'm not going to see much voltage. On the inverse cycle, I'm going to see 2 times the peak voltage of the. Okay, so I'm going to have twice as much inverse voltage on the diode than I did without a filter, because my capacitor is charged up to almost its peak value, and I'm negative on the other side of the diode, so I'm going to see twice the peak voltage. At the end of last semester, we were using capacitors to double voltage and quadruple voltage and triple voltage. So that's basically what's happening here. That capacitor is acting as a voltage doubler as far as the diode is concerned. It's seeing twice the voltage. So on the positive half cycle, I'm positive here. I'm just as positive there. I don't see any voltage across it. On the negative half cycle, I'm positive on the bottom. The capacitor is still charged. I see twice the peak voltage across the diode. Other types of filters. All right, so I can have a pi filter, RC pi filter. I can have an RL filter, or I can have an RC pi filter. Clearly it's called a pi filter because it has 2 legs and something on top. It's called an RC filter because I have an R and a C. And clippers. Okay, so I've got a situation where I've got some device that I cannot allow more than 10 volts to go to it. But I have signals coming into it that periodically go above 10 volts. What am I going to do? Well, I'm going to clip the voltage. So I can have a series clipper, and I can have a shunt clipper. Series means I'm in series with the load. Shunt means I'm in parallel with the load. All right, so here's a series clipper, and I'm clipping off the negative half cycle. That sort of looks like a power supply, half-wave power supply, right? So my first indication is that's the case. Here I've got a shunt clipper, so now I'm shunting voltage power to the ground, and I'm getting rid of that voltage. Now, I'm going to move back for a moment. Am I losing power when I'm blocking it from going through the diode?
At least a little bit.
Yeah, a little bit, but not much. Am I losing power when I'm sending it to ground? Yes. So if I use a shunt clipper, what I'm doing is I'm throwing away half my electrical power. If I'm not paying for it, I really don't care, right? But if I'm paying for it, that might be something I would care about. If I use a series clipper, then I'm not throwing half the power to ground, and now I'm a happier camper because I'm not using as much power. But we still have a problem with our diodes in that they do have some current limits, so we're still going to have to throw in a current limiting resistor so that when the diode's forward biased, it doesn't go and burn up on me. Or I'm going to have to build an extra big heat sink, which costs a lot of money too. That's my other choice. So let's stop this for a moment and ask ourselves, why am I not seeing what I think I should be seeing? Oh, there it is. I see it. Never mind. See this green thing up here?
Mm-hmm.
Yeah, okay. So I see the green thing up there. I was thinking that I wasn't recording, but I am. That'll teach me to think. So now I can have a shunt clipper, and I can throw in a power supply, and now I'm gonna have the whole negative half cycle because it's reverse bias. But in the positive half cycle, I'm gonna stay up by voltage B, whatever it might be, plus the 0.7 drop across the diode. So now I'm clipping off the top half of the circuit. I can put the diode in the other way with a battery and clip off the bottom part of the circuit. So now we have another insult you can use in the lab, U-clipper, something like that. And that would be, or even better, use shunt clipper. That'd be a real insult there. You could be a series clipper too, but that's probably not as insulting as being a shunt clipper. So now I've got a variable clipper. I'm gonna change my voltage, and then I'm gonna change the value of where I'm clipping off. So now we have clipper configurations. And of course, probably chapter 18.7 probably does clippers over again using Zener diodes probably, and so that'll be fun too. So now I can keep the positive half cycle, keep the negative half cycle. I can do it in series, I can do it in shunt, or I can throw in a power supply and keep part of the cycle I'm trying to get rid of. So those are all the positive things I can do. And now we're doing it as a transistor protector. Transient, not transistor, a transient protector. So now if I go too far negative, I end up sending the signal to ground. So now, and if I go too far positive, I end up sending the signal to my 0.5 power supply, and I end up getting rid of bad transients, is what that diode configuration is doing. Voltage spikes that are extreme short duration. So our lifespan is pretty long, right? And our eyesight is even worse. So extremely short, milliseconds. That's not very short, right? But let's say I've got a 100 megahertz Ethernet system going. Is that thing spiking? It's, it's supposed to be plus or minus 3.5 volts or so. Does it ever spike? Well, yeah, it probably does all the time. So I would have some clipper circuit associated with my Ethernet so that when I get the signal through my wire and it gets to my computer, I throw away all those transient things that are happening. And there's lots and lots of them. Oh, now we're up to clampers, and that means we have to do homework because we're only supposed to make it to 18.5 today. And we're at 18.5, so that means I have to quit. Okay, so we'll get out of the transparency, and we'll see whether or not we can solve homework problems without my pen working. And I'm sure I'm talented. If Annette can do it with her fingers on the whiteboard, I can do it with my fingers on this thing, right? All right, so what problem are we looking at? Number 3. Now, what should be happening is that you guys should have all these problems done already, right? And then we could just go home early. I guess that won't work. Anyway, it was just one of those random thoughts I have every now and then. All right, so. All right, I have control of my pad. Okay, so number 3. Determine the peak load voltage for the circuit shown below. Okay, so the voltage, peak, load. Now it says that I'm plugged in. See that little plug signal? That indicates I have 120 volts coming in, RMS. And I've got 12 volts coming out rated. Is that a peak value or is that an RMS value? So that's an RMS value. So we're going to have to go square root of 2 times 12 to get the peak value. And then we're going to have to subtract a 0.7 because we have a diode sitting in the way. Square root 2. Okay, so that's 1.414. Square root of 2 times 12 minus 0.7. And I show 16.3. And I'd probably keep that. 16, well, maybe not. 16.3 volts. And then I'd have to ask myself, how many significant digits do I have? And yeah, I can't keep that many significant digits. So I would probably change it to 16 volts due to significant digits. So I'd say 16 volts. Your line voltage at your house. When was the last time you had 120 volts? You ever measure it? Is it closer to 110? Is it closer to 117? Back in the good old days when we had laptops that were considerably bigger than this one, that had 286 processors in them. That's probably before you graduated from kindergarten. We had one of the computer science guys had one over in his office, and it was blowing its fuse, the power supply fuse. And I would get it, and I'd replace the fuse. Well, the fuse is soldered in. Okay, so I'd go and solder leads on a new fuse and solder it and get it back to him, and it'd blow again. And, well, what the heck? And so I put another fuse in, and I'm not changing the size of the fuse. I put it in. I plug it in my lab. It comes on, and the fuse is blowing on power up for him. So I power it up, it works fine. Okay, I turn it off, I power it up, it works fine. I give it back to him, I power it up, he powers it up, it blows the fuse. Well, what's going on? How is the world, what's his karma? It has to be a karma problem. It's Dan Christensen, if you know Dan Christensen. He's the religion instructor over there, very nice guy, but year older than I am. You're younger than I am? No. I think he's 3 weeks older than I am. Anyway, I go grab my voltmeter. In my lab, I have 120 volts. I have 120 volts because I have my own damn transformer. we have our own transformer in our lab. That way, we can't mess up the rest of the school. Okay, we can short anything we want out. It won't matter. The lights will not go out at the rest of the school. We have our own transformer. Because we have our own transformer, we have our own emergency shutdown button. So we can push the emergency shutdown button, and all power is secured to that transformer, and we don't. And the lab doesn't have power anymore. So when I go out, I do. So anyway, 120 volts. I go into his office, and he has 110 volts. Now it's across the hall. I'm here, he's there, 50 feet away. What's going on? You know, how can this happen? You know, well, as it turns out, his offices have windows. It's the winter, and the girls have heaters under their desk, and they're lowering the line voltage due to their heaters being hooked up. That lowering line voltage, the computer's going to draw the same amount of power. If I want to draw the same amount of power with less voltage, I'm going to have to draw more current. And if I draw more current, I'm blowing the fuse. All right, well, as technicians, there was a time when we fixed televisions. And that was way before any of you guys were born. But coming out of World War II, we trained a whole lot of people to fix TVs. And they'd go around fixing your TV. And when we had tube televisions, a repairman was at the house every 6 months to repair something. And it was back in the glory days when maybe you had 3 channels if you're lucky. Maybe if you're really super lucky and lived in a big city, you could actually pull in 4 channels. If you're out in the country, you didn't even have a TV because you didn't have squat. Anyway, we had associated with that program isolation transformers. So we could work on the televisions and not blow the fuses for the same reason. That's why we had it. So what I did, this isolation transformer would bring in the line voltage of 110 and put out 120. So I put an isolation transformer in his office, plugged it in, turned it on. His laptop worked fine, even though the girls were heating up the other place. How did we get there? Anybody know? Yeah. So that was number 3. Moving on to number 15. Okay, so number 15. I wonder. No, I can't even use my pen doing that. Okay, number 15. Determine the values of voltage peak load, voltage average, and current average for the circuit below. Okay. So I'm center tapped. I have 30 volts AC that it's rated, and I want peak. Okay, so I'm looking for voltage, secondary, peak. I'm going to go square root of 2. Well, that sure is a professional looking square root sign if I ever saw one. Times 30. Is it 30? Yeah, 30 volts. All right, so square root of 2. I'm off again. Square root of 2 times 30. Thank you very much. How come I'm in exact now and it's giving me the square root of 2, 30 to the square root of 2? All right, that's better. 42.4 volts. 42.4 volts. Okay, no. I want the voltage load peak. Okay, so I'm going to voltage load peak. Well, that looks good too, doesn't it? All right, so I'm going to take the voltage secondary peak, divide by 2. divide by 2, and subtract 0.7. So that's my plan. If I could spell voltage, load, peak, that'd be helpful too. Okay, so I already have voltage secondary peak divided by 2 minus 0.7. 20.5 volts, and we'd probably try that one. No, that one doesn't work. No, nice try. No, it's got to have a battery, and the battery's probably dead. And if I can't open it, then I have a vise in the other room though, and I'm sure that I can clamp down on this sucker and get it open.
Or does it just stick into something and charge?
I don't think so. I also have the manuals for it. What's the 20.5 volts? 20.5.
20.5?
Yeah, that's what I got. 20.5 volts.
Yeah.
Is that what you got?
That's what I got.
That's what you got? 20.5 volts. Then we want the voltage average. Okay, so the voltage average is going to be voltage, load, peak divided by pi, right? Voltage, load, peak divided by pi. Or is it divided by... Well, I told you I wouldn't remember that one. Yes, it is. Divided by pi. All right. I lost my mind for a little while. Okay, so second function answer divided by pi. Well, 6.5 volts. That can't be 6.5 volts. Really? How can I have 20 volts peak and my DC be so low?
I think it's supposed to be 2 times voltage load.
I think it is 2. Yes, 2.
Page 581.
Yeah, I'm on page 586. It's 2 times that. Yes, I agree. So 2 times that. I knew it looked small. Times 2, 13 volts. 13 volts. And then I want the current. Is V still equal to IR? Yes, V is still. When will V not be equal to IR? Does anybody know?
I have to think about it.
Probably around the time of the second coming of Christ, because he's supposed to be ushering in a new heaven and a new earth. And with a new heaven and a new earth, we don't necessarily have to keep all the old physical laws. They could all be transformed as well. So if it's going to change at all, it would change then. It might also be different inside the middle of a black hole. So until we get inside the middle of a black hole and try out Ohm's law, that's still a questionable thing. Yeah. It might be that way. But until either of those events occur, we're hanging out in the middle of a black hole or the second coming, and we have a new heaven and a new earth, then Ohm's law will probably be there. So we want the current average. All right, so we're going to take the voltage average, which is 13 volts. And that doesn't look a whole lot like 13 to me. 13 volts, and we're going to divide it by what? 6.2K. 6.2K. So it's going to be something around 2, right? 2 milliamps. Okay, so I got 13 divided by 6200. 2.1 milliamps. Good enough? 2.1 milliamps. Well, that looks like a very professional A there too, doesn't it? Well, we can fix that.
R. I can't see, the lamp is reached.
It is?
Maybe I should change the lamp.
Yeah.
Go.
Yeah.
Get a ladder.
What's in the way? Oh, the,
black mark.
That lamp
Oh.
has reached the end of its useful life.
somebody. So I don't see that, so only you guys can see that. So when you're watching the video, that won't be there, so it won't be an issue. Oh.
See what light is.
Watch the video.
I'm gonna have to.
There, is that better?
Yeah.
All right. Now, why is it that only Chase is awake enough to know that that's happening? I don't know. Beats the heck out of me. Okay, so that was easy enough. 21. Determine the peak and average output voltage and current for the circuit shown. Okay. Number 21. So voltage. What do we want? Voltage, load, peak. The peak and average output voltage. Okay, so voltage, load, peak. All right, so we're going to go square root of 2. All right, that's pretty bad. Square root of 2 times 36. 36. Minus 1.4. Minus 1.4 because I have 2 of them. 2 transistors in the line. Diodes in the line. Whatever I got. Alright, so square root of 2 times 36 minus 1.4. 39.5. 39.5? No? 49. 49.5? Better? 49.5.
Yes.
All right, now we're going to need the voltage average. Voltage average, which is going to be 2 times the voltage peak. Divided by pi. I got an idea. Okay, we're gonna do it again.
Oh wow.
All right, where's the zoom guy? Zoom, zoom. Okay, so voltage AC is 36. 36? 36. No, 36. And we want voltage, load, voltage, load peak. Alright, so voltage load peak is the square root of 2. Where's the square root? Square root of 2 times voltage AC minus 0.7. What? What? Where?
And you have it at 0.14 or 1.4 because it was the two. Right.
Bridge rectifier, so it's
Oh, there's 2 of them.
Right.
Typical. You're complaining about something like that. 1.4. All right. So now we want eval floating point of the guy on top.
Eval?
Yeah. Okay. There we go. 49.5. Excellent. And then we want the voltage load average. All right, so the voltage load average is what? 2 times the voltage load peak divided by pi. Where's pi? There's pi. And then we go eval floating point, the guy on top. 31.5. All right, so do we get 31.5?
Yep.
And then we want the current average. So the current
Bring it up.
average. Okay, is that better? Guys, anyway.
How about we just replace the bulb or reset?
I don't think it can go up. It can go up after I get there. So current average. Current average is the voltage average, voltage load average divided by the resistance. What's the resistance? 10K.
Error.
Here, illegal use of object as the name. Okay. So what is it complaining about?
Is it you're using an already existing thing and trying to use it as a variable? Is that what it's saying?
I don't think so. Okay, it might not like I, so we'll call it I1. Oh yes, I is reserved as an imaginary number. Uh-huh. So, yeah, I can't do anything about that yet.
Oh, okay.
Yeah, so eval F, the guy up above. All right, so the 3.1 milliamps, 3.2 milliamps. Yeah, 3.2 milliamps. Okay, so that work. Does that work better than me trying to scribble it using my pen? That work better?
A little bit.
A little bit?
Anyways.
You might be able to read that.
Yeah.
All right. So, oh, what's the matter? What's the matter? Am I going too
What
fast?
is that? Oh,
31.5 milliamps. No, 3.2 milliamps.
Yeah, 3.2 million. I'd round it up. 3.2.
times or what?
3.2 milliamps.
We get stay on pace here.
Okay,
I'm trying to get.
number 25. The circuit shown below has the following values. Determine the ripple voltage, the DC voltage, and the current going to the load. All right. Okay, so we're gonna do number 25 next. So number 25. Like that? Is that good? So we want to know. We're gonna have to figure out the voltage to the load first. The peak voltage to the load. Okay, so I want voltage, load, peak. Okay, so voltage, load, peak. And what does that equal to? That is equal to the square root of 2 times the 18 volts, 18 minus 1.4. Okay, so, and we want to eval floating point, the guy up above, which I may have been hosed. Okay, so we have 24 volts is our peak load voltage. Now we've got to calculate the ripple voltage. Anybody remember what that equation was for ripple voltage? And yeah, there's a formula for one there, but that's not the one we want. No, the one on 589, I need an inductor, and I don't have an no, yeah, right, the one on 589. Okay, so, but I need the load, the current to the load. All right, so I have to calculate the current to the load first. Okay, so I'm gonna okay, I know the load. Excellent. All right, so I've got the peak load voltage. I want the average load voltage. Voltage, average. Voltage, load, average equals 2 times the voltage load peak, and I misspelled load peak, divided by pi. And eval okay, so the average voltage of the load 13.3. So the current, and again we'll call it I1, to the load average equals voltage. Well, yeah, voltage, load, average, divided by the resistance, which is 820. 820. Okay. And didn't like that, so I'll put a funny thing here and there. Oh, wrong funny thing. Oh, that's better. And eval, the guy above him. All right, so that's going to be 18 point something milliamps. Okay, so we back to the equation. The equation for voltage ripple voltage is going to be the load current. Okay, so I1 load average, and I forgot it already. Times the time between peaks. This is a full wave rectifier, right? So that would be 8.3 milliseconds times 0.0083333333 divided by the capacitance 470.123470. Eval so my ripple voltage is about 1/3 of a volt, 0.3333. All right, so we got this. So there's my ripple voltage. So I calculated the ripple voltage. I just calculated the load current. Now I've got to find the DC voltage. Okay, so voltage DC equals the voltage load peak minus the ripple voltage divided by 2. Is that not so? Wow. Eval. Yeah. That guy. So my DC voltage is going to be 23.9 volts. Can you see that? All right. Okay. Do we do 35? The potential. Yeah. We gotta. Well, I'm going to read 35 to see if we can do it. The potentiometer below is set for diode 1. Blah 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 blah. Determine the peak load voltages for the circuit and draw the output waveform. Okay, this is just a clipper circuit. Okay, I think I can do that. Alright, so I need a couple grounds. And I need a power supply. Power supply. And I need a diode. Three resistors and a diode. And I need a DC power supply. And another ground. And a diode. Alright, do I have enough components? Alright. Alright, so I've got now, this guy is supposed to be 14 volts peak to peak. Alright, so 14 volts peak to peak. So if I'm 14 volts peak to peak, and I multiply that by 0.707, that's going to be 9.9. So if I change this to 9.9 volts, then that'll give me 14 volts peak to peak. And I'm going to send that through a resistor. That's going to be 150. And I'm going to have a battery. And we'll flip it that way. What happened to all my grounds? And we'll put a ground up here. And we'll have a variable guy sitting there. And a ground sitting there. Here's my diode. Diode's upside down. This guy's supposed to be 2 volts. I think. Is he? Oh, he's supposed to be minus 2 volts. Figure out is set so that the diode D1 is at minus 2 volts. How am I going to get minus 2 volts on that guy? Well, we could redraw it, right? Or we could just make this a minus voltage. Yeah, we just make that a minus voltage. 1500. Okay, so there we go. So this is 14 volts. On the positive half cycle, the diode is reverse biased. We expect to see the positive half cycle. On the negative half cycle, we expect to see it down to minus 2.7 volts before it's cut off. Anything negative, more negative than 2.7 is going to go to ground. We have a problem. Okay, so we're going to have to solve that problem before we turn on the circuit. Anybody know what the problem is? Yeah, that's what I thought too. That's exactly what I thought. The problem is, the way we have it drawn, I don't see how we have to get 2 volts on the diode, and before we turn it on. So let's see what we got. Okay, so there's -1. That's going the wrong way. Okay, so there's -2 on the diode. Okay, so now I got -2 on the diode. Oh, you want it connected on the top too? Some guys just are so picky. You notice that? You know, everything was fine, and then we got it connected on the top too. All right, so here we go, there and there. So our what we're saying is that we're going to see something. We're going to see the entire positive half cycle. The negative half cycle is going to be chopped at -2.7 volts. Okay, so that's if I didn't have this turned on, that's what I would say it was doing. And all of you agree with that, so that's all that matters. And so that's what we're seeing. So I have the entire positive half cycle. Do we agree with that?
Yes.
More or less. Yeah, I'm seeing. Wait a minute. I'm supposed to be seeing 14 volts peak to peak. Is that what I'm supposed to be seeing?
Yeah.
Oh, that means 7. All right, 14 volts. So 7 times 0.707. So it should be 4.9, 4.95. All right. So this should be 4.95. And we'll change the scale. Too far. Too far. Still can't see it all. Oh, we'll bring it down some. All right, there we go. Is that fine? So we bring this guy over, and we should just see about 7 volts peak. And we still need a little bit more. That's probably okay. Is that okay? There's going to be some voltage. There's going to be some voltage drop across this resistor, right? So why don't we just come over here and look and see if it's okay? I don't know. Beats the heck out of me. And then we'll change this to there. All right, that'd be better. All right, you like that better? Change this to all right. Drop this down. Now we can't see the whole thing. Darn. Okay, so now we can see the whole thing, and I'm seeing. All right, there's my 7 volts peak to peak, like I'm supposed to, but I only have 6 point something across the other guy, and then we said we were going to go -2.5, 2.7. And there's my -2.7. So, lucky guess. Yeah, too easy to guess, right? So that's yeah, lucky guess. All right, next problem is 45. 45. The input of the circuit shown in 60B. 60B. Determine the peak output voltage of the waveform. I guess that can wait. That can wait until tomorrow. Yeah, that can wait until next week. Okay. Thank you, gentlemen.
That's pretty neat.